Hi, I'm Dor Atzmon, a PhD student at Ben-Gurion University. My advisors are Ariel Fellner and Ronnie Stern, and this research is called Probabilistic Robust Multi-Agent Pathfinding. This is joint work with Ronnie Stern, Ariel Fellner, Nathan Studevant, and Sven Koenig. In multi-agent pathfinding, we find a plan for multiple agents such that agents do not conflict. In reality, agents may experience delays while executing a plan. Thus, while there are no conflicts in the plan, agents may still conflict. In this research, we want to find a solution that is robust to delays with high probability. Let's start by defining formally the classical multi-agent pathfinding problem. The multi-agent pathfinding problem is defined by a map with n locations and a set of agents where each agent has a start location and a goal location. At each time step, an agent can either move to an adjacent location or wait in its current location. The task is to find a path for each agent from its start location to its goal location such that agents do not conflict. And the target is to minimize the sum of travel costs. Let's see a possible solution for this example. First, both agents move. Then, one of the agents must wait to avoid a conflict. Now, both agents can move. And finally, only the blue agent moves, and a solution with a cost of 7 is achieved. The probabilistic robust multi-agent pathfinding problem extends the classical problem. In this problem, there is an additional input. PD is the probability for experiencing a delay while performing a move action, and P is a probability threshold. P0 of pi denotes the probability for no conflicts while executing plan pi. We say that plan pi is p-robust if and only if the probability P0 of pi that no conflicts will occur is larger than or equal to the probability threshold P. In this problem, we want to find a p-robust plan. Let's start by solving the classical problem, and afterward, we'll solve this problem. Conflict-based search, or CBS, is a commonly used multi-agent pathfinding solver. Let's see how it works. First, we find a path for each agent from its start location to its goal location. We put this plan in the root node of a binary constraint tree, as well as an empty set of constraints. In this example, the path of the red agent is S1ACG1, and the path of the blue agent is S2BCG2. We then identify conflict in our plan. Here, we can see that both agents occupy location C at time step 2. As this plan contains a conflict, it is not a valid solution to the problem. To resolve this conflict, one of the agents cannot occupy location C at time step 2. We create two new nodes. In the left node, the red agent is prohibited from occupying location C at timestamp 2, and in the right node, the blue agent is prohibited from occupying location C at timestamp 2. We now calculate a new path for each of the constrained agents. This new path must satisfy all constraints of the corresponding node. Finally, we perform a best-first search on the constraint tree, expanding the node with the lowest cost first. For instance, we can expand the left node and a solution is found. In this research, we would like to find a p-robust solution. So how can we adjust CBS to find a p-robust solution? In the p-robust version of CBS, PRCBS, we also start by finding a path for each agent. However, step 2, in which conflicts are identified, is slightly different. In multi-agent pathfinding, there is a conflict when two agents are at the same location at the same time step. In p-robust, there is a potential conflict when two agents are at the same location, even in different time steps. In this example, the red agent is at location C at time step T1, and the blue agent is at location C at time step T2. A potential conflict exists because there is some probability that the red agent will be delayed such that the two agents will conflict. Instead of conflicts at step 2, we identify potential conflicts between the agents. The second modification is between step 2 and step 3. Right after step 2 and before step 3, we need to determine whether the node is a goal node or not. In CBS, it's easy. We know that a conflict-free plan is a valid solution. In P-robust, it's more difficult, as a solution may contain potential conflicts. We suggest two ways to verify whether a solution is P-robust. We call the first verifier the deterministic verifier. The deterministic verifier searches possible sets of delays, calculates the probability for no conflicts, and verifies mathematically whether the plan is P-robust. The second verifier is called the Monte Carlo verifier. The Monte Carlo verifier executes simulations to determine the probability of no conflicts occurring, and then it performs a statistical test to verify whether the plan is P-robust. The last modification we need to make is at step 3. After we determine that a given node is not a goal node, we resolve one of the conflicts. In CBS, we set a constraint on the agents to avoid the conflict. In CBS, to resolve the conflict, we say that either the red agent or the blue agent cannot occupy location C at time step 2. In P-robust, we create two similar nodes. In this example, we say that either the red agent cannot occupy location C at time step T1 or the blue agents cannot occupy location C at time step T2. However, this is not enough for obtaining an optimal solution. In the previous modification, we saw that a P-robust solution may contain potential conflicts. By resolving a potential conflict, we may lose the optimal solution. Therefore, we create a third node that forces the potential conflict to occur. This can be done by imposing a positive constraint that forces the red agent to occupy location C at time step T1 and also forces the blue agent to occupy location C at time step T2. In this way, we will not lose the optimal solution. So we have three modifications. First, instead of conflicts, we identify potential conflicts. Then, we verify a solution either by the deterministic verifier or by the Monte Carlo verifier. And finally, if the node is not a goal node, we create three nodes. Two nodes to resolve the conflict and one node that forces the conflict to occur. In addition to this algorithm, we also suggest a suboptimal greedy version of this algorithm. Due to lack of time, the relaxations made by this version are not described in this presentation. We tested CBS, the greedy version of PRCBS, and PRCBS with our two verifiers for different values of P and delay probability of 0.1 on an 8x8 empty grid with 8 agents. We can see that the Monte Carlo verifier is faster than the deterministic verifier, and the greedy version is faster than both, but is not optimal and has a higher cost. CBS is the fastest, but does not consider the value of P. We also performed an experiment on a larger map with 10, 20, and 30 agents. Here, we compared CBS, the greedy version, and another algorithm called KRCBS. In addition to the runtime, we also measured the percentage of 50 simulations with no conflicts. To measure it, each solution returned by each algorithm was simulated 50 times. We can see that here also CBS is the fastest but causes many conflicts. When tested with 30 agents, on average, only 37% of the simulations had no conflict. We can see also that PRGCBS causes the fewest conflicts. We talked about a P-robust plan, and the challenge was to find such a plan. We saw that such a plan can be found by the P-robust CBS algorithm, which can use one of the two verifiers we proposed. A suboptimal solution to the problem can be found by the greedy version of the algorithm. P-robust solutions may consume runtime, but cause fewer conflicts between the agents. Future work can adapt other solvers to find P-robust solutions and can integrate P-robust solutions with execution policies. Thanks for listening.